Student friends, in last lecture we already discussed on the various factors which are effects on the base strength. We know the first factor which affect on the base strength is the availability of lone pair of electrons. When the base having the lone pair of electron with us and this lone pair of electron is available for the donation or easily available for donation, then the base strength is increases. The second factor is the electronegativity of base. When the base having the more electronegative, then the tendency to donate the lone pair of electron is less, and ultimately the base strength is decreases. Third point, the structural effect on base. The groups which are attached to the base, which gives the minus I and minus R effect, then the electron density around the nitrogen is decreases, or electron density around the nitrogen or base is decreases, and then ultimately the base strength is decreases. When the base having the groups which gives the electron donating inductive effect and electron donating resonance effect, then the base strength is increases because the conjugated acid is well stabilized. And the last factor is important, that is the nature of solvent. The solvent having the two types, the polar and non-polar solvent. But when the conjugated acid of that particular base is the charged species, then the polar solvent is solvated by this conjugated acid, and then conjugated acid is stabilized in a polar solvent, and that's why the base strength is increases. But when base itself is a negative or charged species, then base itself solvated by the polar solvent, and then the acid base strength is decreases. So that's why when the base having the charged species, the non-polar solvent or in non-polar solvent, the base strength is increases. Then after the factors which are affect on the strength of bases or base, so we take one first example and we compare the basicity of aliphatic bases. So that's why we take the first example, ammonia. You take a methylamine, you take a dimethylamine, and you take a example, this is a trimethylamine. We remember this is the primary base, this is the secondary one, and this is a tertiary base. So in case of ammonia, there is no, or nitrogen having the hydrogens, so hydrogen don't have the electron donating or withdrawing abilities. But in case of, in other, these three example, primary, secondary and tertiary base, in primary there is one methyl group donate the electron to nitrogen, and that's why it gives the plus I effect. So ultimately ammonia is weaker than all the bases, means primary, secondary and the tertiary. What happens in case of the secondary base or dimethylamine? There is such type of 2-methyl group is there. Methyl group is act as electron donor, and it gives the plus I inductive effect or electron donating inductive effect. Then in case of tertiary amine or trimethylamine, such a type of 3-methyl groups, and this 3-methyl group gives the plus I effect. So when we compare the plus I effect of these three bases, primary, secondary and tertiary, here is a plus I effect is less because one methyl group donate the electron. In this case, secondary amine or dimethylamine, there is two such methyl group is there, they donate the electron and gives the plus I effect. So in secondary amine, the strength of plus I effect is more. But what happens in case of the tertiary? In case of tertiary base, such type of 3-methyl group is there, and this 3-methyl group donate the electron and gives the plus I effect. So where the plus I effect is more? In a tertiary base or trimethyl amine. When only we compare the electron donating inductive effect, ammonia don't have the such type of methyl group, so that's why in ammonia there is no electron donating inductive effect is there. But in primary amine, the electron donating inductive effect is less. It is increased in secondary amine and it is more in the tertiary amine. When only we compare the basicity of these 4 bases according to the inductive effect or electron donating inductive effect, then tertiary amine is a more stronger base. But actually tertiary amine is not a stronger base, but the secondary amine is a stronger base than the tertiary one. So that's why out of that 4, which is the weaker one? The ammonia. Then the methyl amine, because the inductive effect is less. When we compare the secondary amine and tertiary amine, what happened? Tertiary amine having the more inductive effect, secondary amine having the less inductive effect. We compare the only inductive effect, the tertiary amine is a weaker, stronger base than the secondary one, but actually this is not happen. The secondary amine is a more stronger base than the tertiary one, so that's why there is a introduction of new group is there, and that is called the solvation. Means what? When you take this is a secondary amine, and secondary amine there is a formation of conjugated acid of secondary amine. Then this is tertiary amine, we form the conjugated acid of tertiary amine. And this conjugated acid in case of secondary amine, what happen? This conjugated acid is stabilized by solvation of water molecule. So what happened? Here such a type of 2 water molecule is solvated, this conjugated acid. But in case of tertiary amine, only such type of 1 water molecule is solvated by this conjugated acid of a tertiary amine. So what happened? When we think about secondary amine, the inductive effect is less than the tertiary one, but solvation effect is more. So conjugated acid is more stabilized as compared to the tertiary amine. So when we compare the basicity between secondary and tertiary amine, so what is important? Inductive effect as well as the solvation effect by the polar solvent. Both factors, they are the important, and combinedly there is a inductive effect and the solvation effect. So what happened? Here the 2 inductive effect due to the 2 plus I effect due to the 2 methyl group, and solvation, this 2 water molecule is solvated by the conjugated acid. So the combined effect of inductive effect and solvation effect, a solvation of conjugated acid, both effect makes the secondary amine is a stronger base than the tertiary amine. So when we compare the basicity between secondary and tertiary amine, then we consider the inductive effect as well as the solvation of conjugated acid by the polar solvent. So that's why out of these 4 aliphatic bases, secondary amine is the more stronger, then tertiary amine, then the primary amine, and then the ammonia. So in this way we compare the basicity in case of aliphatic acid, aliphatic bases. Then you take a next example. Amides are extremely weak bases. We write here the amides. So why the amides are weaker bases or extremely weaker bases is there? Because we remember amide having the NH2 group nitrogen having the lone pair, but we remember in case of amide NH2 group is attached to the carbonyl group, and this carbonyl group gives the plus I effect as well as minus I effect as well as minus R effect. Because what happened, this carbonyl group not only gives the electron withdrawing inductive effect, but it also gives the electron withdrawing resonance effect is there. So what happened when we write a resonating structure of this amide, this lone pair on nitrogen is delocalized on a carbonyl carbon, and when this lone pair on nitrogen is delocalized on carbonyl carbon, then this lone pair is no more available for donation to the H plus or for the donation to the other species. So when we see the resonating structure of this amide, what happened? Nitrogen get a positive charge, and when nitrogen get a positive charge, then it is not possible to donate the lone pair of electron, or lone pair is not available for donation because this lone pair on nitrogen is delocalized to the carbonyl carbon. So that's why carbonyl carbon withdraw the lone pair of electron or take the lone pair of electron from the nitrogen, and that's why it gives the minus R as well as the minus I. So that's why amides are neutral in nature, so amides are very extremely weak bases because the lone pair on nitrogen is not available for donation, but it delocalizes on a carbonyl carbon, and carbonyl carbon gives the two types of effect. There is a minus I and minus R. We already discussed when there is a minus I and minus R effect is there, then the base strength is decreases. Then why thalamide is acidic in nature? The next question or next example, the thalamide. We write the structure of thalamide. The thalamide having the nitrogen, even though it is acidic in nature. Why it is acidic in nature? We remember well, this is nitrogen, and nitrogen in both the sides is attached to the carbonyl carbon. And we already know when there is a carbonyl carbon is there, so this carbonyl carbon gives the minus I as well as the minus R effect. So that's why what happened, this lone pair on nitrogen is delocalized on both the carbonyl carbon. This lone pair is either delocalized on this carbon or it may be delocalized on this carbon. So that's why lone pair on nitrogen is delocalized on both the carbonyl carbon. So that's why both the carbonyl carbon gives the minus I and minus R effect. And so that's why there are more and more minus I and minus R effect is there. This makes this compound acidic in nature. So because what happened, when you take this thalamide and then they are treated with a base, then it easily abstracts the proton. And when it easily abstracts the proton, nitrogen get the negative charge this way. And when nitrogen get the negative charge, then this conjugated acid it stabilizes. So why this conjugated acid is stabilized? Because this negative charge is delocalized on both the carbonyl carbon. And when the negative charge is delocalized on both the carbonyl carbon, so this is a conjugated base, not a conjugated acid, sorry. This is a conjugated base. Because what happened, this is a thalamide is acidic in nature. Why it is acidic in nature? We already discussed. But what happened, after this thalamide we treat in a base, it abstracts the proton, then nitrogen get a negative charge and we get a conjugated base. And this conjugated base is well stabilized by these two carbonyl, and both the carbonyl group gives the minus I and the minus R effect. And we already discussed when there is a minus I and minus R is there, the conjugated base of acid is well stabilized, and ultimately the thalamide is acidic in nature, even though it having the nitrogen. Then the next example, we think about a gonadine, and we write a structure of gonadine. We take this one, this is the structure of gonadine. What happened in case of gonadine? And we remember, when gonadine take the H plus, then there is a formation of this is the conjugated acid. And we already known this conjugated acid is well stabilized by these two NH2 group. Because what happened, this two NH2 group is there, this is donate the electron, and this conjugated acid is well stabilized by the delocalization of these two electrons, delocalization of the electrons which is available on nitrogen. So that's why we write a resonating structure like that. This is the NH2 and we write the NH2. So similarly, the lone pair on nitrogen in second NH2 group is also taking part in a delocalization. So conjugated acid is well stabilized, and when the conjugated acid is well stabilized, then ultimately the strength of the basic strength of the gonadine is more and more. Then you take a next example and we compare the two compounds, and we compare these two compounds. First one, the aniline, and you take a cyclohexylamine, and in this case aniline is much weaker base than ammonia or cyclohexylamine. What is the reason? So we remember this NH2 group and this NH2 group. So in case of aniline, this NH2 group is attached to sp2 carbon, and we know sp2 carbon gives the minus I effect. But in cyclohexylamine, this NH2 group is attached to the sp3 carbon, and sp3 carbon gives the plus I effect. So what happened? In this case we remember, in ammonia there is a minus I effect due to sp2 carbon, but in cyclohexylamine there is a plus I effect due to sp3 carbon. So NH2 group is attached to the sp2 carbon, it gives the minus I effect. In second case, in cyclohexylamine, NH2 group is attached to the sp3 carbon, it gives the plus I effect. So we know when the plus I effect is there, the base strength is increased, minus I effect is there, the base strength is decreased. This is the first reason. But what happened in case of aniline? In case of aniline, what happened? This lone pair on nitrogen is delocalized on a ring system through the resonance. So we able to write a resonating structures, and in this way we write a resonating structure. The negative charge is delocalized on a ring system. So such a type of resonating structure we able to write, etc. So what happened here? In aniline, this ring system gives which type of effect? It gives the minus R effect. So ultimately, in aniline what happened? NH2 is attached to the sp2 carbon, it gives the minus I effect. That is the first reason. And in second case, this lone pair of nitrogen is taking part in a delocalization through the resonance on a benzene ring system. So that's why we write a resonating structures like that. So that's why this ring system gives the minus R effect on a NH2, and so that's why in aniline there is a minus I effect due to sp2 carbon, and lone pair is delocalized on a ring system. So that's why ring system gives the minus R effect due to minus I and minus R effect aniline is a weaker base, much weaker base than the cyclohexylamine. Then we discuss the next example, and this is the last one regarding the base, and we write the 2,4,6-trinitro-aniline. This is a 2,4,6-trinitro-aniline, and we write its derivatives. This is a 2,4,6-trinitro NN dimethyl aniline. So we remember here, this second one is a more stronger base than the first one, or 2,4,6-trinitro-aniline is 40,000 times weaker than 2,4,6-trinitro-NN dimethyl aniline. So what is the reason behind that? Because in various examples of acids and bases, the various structural effects, they affects on the strength of acid and bases, like an inductive effect, resonance, hydrogen bonding, we already discussed. But in this case, the new effect is there, and that is a structure, or that is a steric effect. So in between these two examples, the steric effect is play a very important role to decide the basicity of these two compounds. So that's what happened in case of the 2,4,6-trinitro-aniline. This compound is a planar, means all the atoms and ring system, they are present in a single plane, and that's what happened. This lone pair of nitrogen is delocalized on a benzene ring. Again, these three nitro group taking part in a delocalization, and that's why these three nitro group gives -I and -R effect. So what happened? In case of 2,4,6-trinitro-aniline, this ring itself gives the -R effect. Then on that ring system, there are the three nitro groups are attached. This nitro group is act as electron withdrawing groups, and they withdraw the electron by the resonance as well as a inductive effect. So nitro group gives the -I as well as the -R effect. And again, what happened due to this lone pair on nitrogen in case of 2,4,6-trinitro-aniline is delocalized on ring system as well as three nitro group. So that's why this lone pair is not available for donation to the H plus or other species. And when in first case the lone pair is not available for donation, ultimately it is a weaker base. There is no doubt it is a weaker base. But what happened in case of the second case? Instead of there is a two hydrogen in this NH2 group, we replace by the methyl group, and so that's why we write here 2,4,6-trinitro-NN dimethyl aniline. And what happened in case of this? We remember this is the nitro group, this is a methyl group. Here is a methyl group and nitro group. The both group having the large size, they are come closer, and when they are come closer, then there is a steric repulsion, or we call steric repulsion or steric hindrance. And this methyl and this nitro, they are come closer, there is a crowding is there, and when there is a crowding is there, then steric repulsion between this methyl and nitro. To avoid the steric repulsion, what happened? To avoid the steric repulsion or to minimize the steric repulsion, the bond between this carbon and nitrogen is rotate. This bond between carbon and nitrogen is rotate. And when the bond between this carbon and nitrogen is rotate, then what happen? This both the methyl group, they are perpendicular to the plane, which carries benzene ring and 3 nitro group, and this is a nitrogen. Means we suppose we consider this is a blackboard is a plane, and in this plane benzene ring system, nitro group, 3 nitro group and nitrogen, they are present in a single plane. And what happen? One methyl group is below the blackboard and one methyl group is upward or front side of the blackboard. So ultimately what happen? These two methyl group, they are plane perpendicular. Means in 2,4,6 trinitro and then dimethyl aniline, due to the steric repulsion or to minimize the steric repulsion, the bond between carbon and nitrogen is rotate, and after rotation of the bond between carbon and nitrogen, the planarity of molecule is lost. Means all the atoms or all the groups, they are not present in a single plane. Means this methyl and this methyl, they are perpendicular to the plane. So ultimately when compound lost the planarity, then there is a resonance effect is never possible. So that's why what happened in this case then? Compound lost the planarity and ultimately this lone pair is only available for donation to the H plus or other species. So that's why in case as like 2,4,6 trinitro aniline, lone pair is delocalized and nitro group as well as the benzene ring system. But here the planarity of the molecule is lost. There is no resonance, and when the planarity is lost, then this lone pair on nitrogen is not delocalized on nitro group as well as the benzene ring system. It only available to the donation to the H plus, and ultimately the 2,4,6 trinitro and then dimethyl aniline is that is a 14,000 times stronger base than the first one. So in this case, in two examples, which is important? In this case, the steric effect or steric repulsion or steric hindrance is very, very important. So what is meant by the steric repulsion or steric hindrance? Means when there is a steric repulsion between the two groups in a space. When the groups, they are come closer, the size of the group is increases, then instead of attraction, there is a repulsion is there, and we call the steric repulsion. So due to the steric repulsion, the 2,4,6 trinitro and then dimethyl aniline is very, very stronger base as compared to 2,4,6 trinitro aniline.